All right. Hello to those watching this on the video. I've already said hello to all of you. Hello again. Hello to those watching the video. This is a revision seminar for Maths 1B at Adelaide University in summer semester 2026, the first revision seminar of the new university, but with a legacy course from the old university. So, you know, a trip one step at a time. Okay, so I've been given some requests and we'll give them a go. Okay. Well, let's see how I go. Okay, cool. I'll put the chat back on. If something appears in the chat and I haven't talked about it, can you people in the room let me know? It's your way of helping me to make sure the people online don't get left out. Okay. So series are things that look like this. Something like that, maybe with an N. Doesn't really matter what the letter is. And this could be any formula that involves N or doesn't. And the big question of series is whether they converge. And converge means that if you keep doing the running total and keep adding on more and more and more terms, that running total approaches a limit. That's what it means to converge. I believe the official word for running total is partial sum. But running total is a word that I already know, so it makes more sense to me. So technically, method 0 for figuring out whether a series converges is to figure out a formula for what the running total is and then do the limit of that as n goes to infinity. That is not easy, and there is pretty much one series where the proof of that that's involved in the proof. But you can always do that. So, like, you know, running total, partial sum, and do the limit as n goes to infinity. That is method 0. No one will use that, but I have seen an assignment/exam question that says, here's a series, note that its partial sum has this formula, does it converge? And so they've done that part of the work for you. So it's worth noting that a lecturer will sometimes go all the way back to the definition and do the bit where they find the formula for the partial sum for you. And then it's just a limit question. Okay, so then the other ways of doing this, that's gold standard. It will always work if you can find a formula for the partial sum. But most other methods are designed by comparing it to a series that we already know whether it converges or not. And so method number 1 is to just happen to recognize a series. And the classic series that you're supposed to be able to recognize in this course are that one, which is called the harmonic series, the sum from 1 to n of 1 over n. 1 to infinity of 1 over n. And this definitely does not converge. Do they use the word diverge in this course? You don't have to do anything. No one will ever ask you to prove that this diverges in an exam. It's too hard. It definitely diverges. If you just see it, you go, diverges, because it's the harmonic series, don't have to do any more working than that. It doesn't have to start at 1, it could start anywhere, it could start at 10,000, it will still diverge. because it's the infinity part that makes it diverge. So it might have n plus 1 here. That doesn't matter. That's just offset by 1. It doesn't really matter whether it's n plus 1 or n plus 5. It's all good. Okay, so that's your classic harmonic series. There is the same one but with minus 1 to the n. It may be that this is an n plus 1 and this is an n, or that they don't match, but it doesn't matter. This is called the alternating harmonic. And that converges. Yay! To, I believe, ln2, if I recall correctly. Anyway, and then the other series that you're supposed to just recognise are all Taylor series. So some of them you didn't meet until after you saw Taylor series, which was after the series bit, and some of them you met before. So there's this one, and so these ones have a letter X in them, and that's standing for any number at all, and no matter what that number is, it'll definitely converge or diverge depending on the rules. So there's the one that goes like this. Some number to the power of n, that's a geometric series. And it converges if the x is less than 1. The absolute value of x is less than 1. And it diverges if the absolute value of x is greater than or equal to 1. Cool. I missed one. Damn it. That's all right. Put it on the next page. So this is the one where if you have a number in this spot, then you decide whether it converges or diverges based on this information. And the reason it diverges when x is more than 1 is that imagine that was 1.5. You get 1.5 to the 1 plus 1.5 squared plus 1.5 cubed, and 1.5 to the various powers just get bigger and bigger, and you just keep adding on bigger and bigger numbers, and it just becomes infinity. But if a number is less than 1, then its powers get smaller and smaller. Like a half squared is a quarter, and a half cubed is an eighth, and so the numbers you keep adding on are smaller and smaller, and so overall they just don't get past a certain spot. If you keep adding less and less and less, sometimes you don't get past a certain spot. How are we feeling about all this so far? So, secret thing, most series that you are given in this course will be at least partly a geometric series. And it's worthwhile if there are powers with exponent, with the n in the exponent there, to try and do some algebra to get as much of it in numbers in the brackets and n in the exponent. Get as much as possible like that, and then you'll be able to see whether it's a geometric series, and if it is, whether the thing inside is less than 1. That's the strategy. Yeah. Okay. There's this one. So in this one, it's not an x that you replace with a number, it's the letter p here that you replace with a number. And this is called a p series. I don't like when things are named after a letter because you could have put a different letter in that spot, but anyway, that's the way it is. And a p series, well, if p is 1, then it's the harmonic series and it doesn't converge, it diverges. And if p is anything less than 1, then it will also diverge. But if p is anything more than 1, it'll converge. And this p is less than 1 includes p being a negative number. Anything less than 1, including all the negative numbers, it'll definitely diverge. And this p doesn't have to be much more than 1. It could be 1.0001 and it will still converge. That's the idea. Classic. I think there's formulas what they converge to. The one on n squared, I was told by my Maths 1B lecturer, converges to pi squared on 6. Yeah, I remember vividly him saying, and that converges to pi squared on 6, and I think that's just ace. That was Nick Buchdahl, my first year maths lecturer. Yeah. Very few things I remember from 25 years ago, but that is one of them. Okay. No. Oh, God. 27 years ago. Good-o. So, these are the classics, and there are two more that came later, but it's worth putting them in the list of series you're supposed to recognise. So it looks like a geometric series, except that you divide by n factorial. And this is the Maclaurin series for e to the x. Did they use the word Maclaurin series in this course? They use that phrase? Good. That means it's a Taylor series with centre 0. And it always converges, doesn't matter what x is. Makes absolutely no difference what x is, it will always converge. So that n factorial converts it from a geometric series which only sometimes converges to this thing which converges all the time. So if you see that, something that's a mixture of powers and factorials, it's pretty... Just check to see if it's exactly this one, and then it's the Maclaurin series for e to the x. And there are two other Maclaurin series that you're supposed to know. Well, I don't know. Some lecturers expect you to and some don't, so it's worth hedging your bets. And they are also Maclaurin series. And they look very like the one for e to the x, except they have a minus 1 to the n in them. And what you have in these two spots is the odd numbers in one of them and the even numbers in the other one. So one of them will be this. That's the Maclaurin series for cos x. Let me just check. When n is 0, we get a 1. Okay, cool, that's correct. And they also always converge. No matter what x is. I don't know if that's going to be there, but I don't know. I have had people in second year courses who expected me to remember that, even though it technically wasn't expected to be remembered in first year. But they are the same as the ones for e to the x. Except that the cos one has the even numbers because it's an even function, and the sine one has the odd numbers because it's an odd function, and they alternate between plus and minus. In case you're wondering, if you don't have the minus 1 to the n's, then it becomes cosh and shine instead of cos and sine. So, magic. So they are the series you're supposed to recognise. The most likely thing to happen for people who are not, psychopaths writing your exam, is that it will be one of these ones, if you're supposed to just recognise it. I'm going to add one thing to this. The geometric series is also a Maclaurin series. It's the Maclaurin series for 1 over 1 minus x. There are only a small number of series that you know what they add up to, what the sum is. So if your lecturer says, here is a random series, what is its sum? You're almost certainly it's a geometric series. And doing some working to make it into a geometric series is what you need to do. I have lots and lots of examples of that in the various revision seminars over the years. So I may skip that for the moment. I can come back to it if I have time. This happens all the time in lots of different maths things. You get taught about a thing and there's rules for deciding, but there's also a few things that you're just supposed to know. Happens with subspaces as well over in algebra half. Same deal, there's the laws, 3 laws, but there's some that you're just supposed to know by looking at them. And this is the same thing. Okay, I should number my pages. So after you've got recognised it as a series, there are 3 tests. The first one isn't written in your notes as if it was a test, but it is. But it's a test that can only tell you whether something diverges, it can't tell you whether something converges. And in your course it's called the necessary condition for convergence in your notes. So when a mathematician says something's necessary, it doesn't mean that this thing, if it happened, for something to converge, this thing has to happen. But just because it happens doesn't mean it's guaranteed to converge. Okay? So for something to be a Dalmatian, it must have spots, but not all things with spots are Dalmatians. It's the same idea. So it can only tell you whether something diverges, because if it's true, it might converge, but you still don't know. That's the idea. So you get a sum like this, and it's got terms. It doesn't matter where it starts, but one's just easier in my mind. And this is usually a formula, not just an a sub n. It might have n squared plus 1 over blah, blah, blah. And what you do is you say the limit as n goes to infinity of the an. So you're not doing the running total, you're just removing the sum sign and doing the limit of just that bit. That limit of the individual terms, if it doesn't go to 0, then it can't converge. If that's not 0, then it diverges. If it is 0, then it's possible that it will converge, but you still don't know. Or doesn't exist. If the limit is 0 or doesn't exist, then it definitely diverges. If the limit is 0, you still don't know whether it converges or not. That's an important thing to know. Some people call the test failing, it just doesn't tell you anything. So just really need to do an example to ram this point home. Gosh, that noise is fabulous. Something is dying a long, slow, painful death. So this series, it's a perfectly good series. If I put n equals 1 in, I get 2 over 2 squared, which is a half. And if I put n equals 2 in, I get 4 plus 6, 6 over 9, which is 2/3. And I put n equals something else in, n equals 3 in, I've got 12 over 16, which is 3/4. So this number's getting bigger and bigger. So my idea is that it's probably not going to converge because the number just keeps getting bigger. It's going to have to get smaller. But I have to be sure. And so I'll do the limit of this as n goes to infinity. So the limit as n goes to infinity of n squared plus n over n plus 1 squared. And I chose this as well because it gives important lessons about how to do limits when there's this sort of thing going on. It's got a polynomial on both the top and the bottom. If I expand out the top, it's an n squared. If I expand out the bottom, there's an n squared there too. So the biggest power of n I see anywhere is n squared. So I'm going to divide the top and the bottom by n squared. So just to be absolutely clear for people who are reading this without without actually watching the video, I'm going to be absolutely clear what I just did. I'm allowed to divide the top and bottom by any number that's not 0, right? And n is the numbers from 1 to infinity, it's totally not 0, so I can do that. And so I'll get 1 here and 1 on n squared here. And when you do powers expand across division, and so this is the same as n plus 1 divided by n squared. I wouldn't always show that step. And now as n goes to infinity, that bit and that bit both go to 0. Yep.
So you n in the numerator at the start.
I did too. So that'll be a 1 on n there. When I divide by n squared, the n divided by n squared will be 1 on n. Thank you. As I've said multiple times, I wish I had a mistakes fairy in my exam who would do that sort of thing, but I do not. And that both go to 0 as n goes to infinity, so I get this, which is 1, which is not 0, so it diverges. Yay! Just a little what if here. What if that n squared hadn't been there? What would have happened then? So I've got two people saying things. I've got divide by n top and bottom, and the answer will be 0. They are both correct. So if I could have divided by n squared, and I would have just got 1 on n on 1 plus 1 on n squared. That would have been fine. It's supposed to divide by the biggest power of n you see anyway. And so I would have gotten down to here, and it would have come out to 0, and it would be unknown. It doesn't necessarily converge. I don't know. But it would at least be worthwhile the thing to try. Secret, it will in fact not converge, because it will be approximately 1 on n, like an n on the top and an n squared on the bottom is about 1 on n, which is the harmonic series, so it's not going to converge. But there's a formal way of doing that, which they don't teach you in this course, so they wouldn't expect you to make that reasoning in your exam. N plus 1 over n plus 1 squared, perfectly fine. You'll cancel out an n plus 1 and it'll be 1 over n plus 1, and that's the harmonic series. Okay. Feeling okay about that? The reason I have this, I wanted to do this as well, is I want to make a point later when one of the later tests. There's a second test, which is test number 3 in my list, which is the alternating series test. Does this sound familiar? Okay, good. I just have to keep checking in case they cut something from the curriculum without telling me. The alternating series test is only and specifically for alternating series, which are ones that have a minus 1 to the n in them. And so it has to have a minus 1 to the n. There can be whatever other crap you want, but it must have an alternate. It could be n plus 1. Doesn't really matter. It just has to alternate between plus and minus as you go along. So it's worth just subbing in to just see whether it alternates between positive and negative. And the alternating series test requires 2 things to happen. Well, technically 3 things. So the first thing is that it has to have a minus 1 to the n. It has to be alternating. And then the bit without the minus 1 to the n, the positive bit, that has to be, the limit of that has to go to 0. Obviously, because the limit of that does definitely have to go to 0. It won't converge based on the previous one. And also, not just go to 0, but go to 0 in such a way that each term is less than the one before. At some point, Bn is greater than Bn plus 1 is greater than Bn plus 2 forever. So decreasing. It is technically possible to go to 0 by going up and down. You can go like down to a half and up to a third sorry, wrong way, down to a third and up to a half, down to a quarter, up to a fifth, down to, and go that way, and it will definitely go to 0, but it's not going to 0 smoothly. So it has to be properly decreasing, and if that's true, then it'll converge. Nope, the individual terms, without the minus 1 to the n. The running total will actually flip-flop back and forth because of the pluses and minuses. So it'll go up and then it'll go down, go up and then it'll go down. But the amount that it goes up and down by has to be decreasing as you go. The picture that goes with it is that you've got like the n, and that goes like up, down, up, down, up, down, because it alternates between positive and negative, and it eventually gets to 0. But then when you do the running total, the running total at this point is here, and then it went down a bit, and then it went up a bit, and then it went down a bit, and then it went up a bit, and it went down a bit, and then it went up a bit, and it keeps going up and down by less and less and less until it settles down. That's the idea. The individual terms alternate between positive and negative, but the running total alternates between going up and going down. Classic. So that's why I know that the alternating harmonic series converges, because 1 over n just keeps getting smaller and smaller. A perfectly decreasing function, and it's alternating, and 1 over n goes to 0. So those three things have to happen, and yes, it converges because of the alternating series test. But I would work perfectly well with an n squared there, or even with a root n, that would work perfectly fine as well. So even though the root n doesn't match with the p series, if there was a half in this spot, that would not converge. But with a minus 1 to the n on the top, it will, because of the alternating series test. So pretty cool, I think. But you'll only do it if there's a minus 1 to the n in the series. Feeling okay about that? All right. And then the last test is the most powerful of all, and it is called the ratio test. And the ratio test is specifically designed for things that give you geometric series and Maclaurin series for e to the x vibes. So things that have powers and factorials, alternate ratio test is very good for those. So it's great for powers and factorials. Sucks for rational functions. Alternating series will completely, ratio test will completely suck for this kind of thing. So sucks for Pn on Qn, that sort of thing. Ratio test just will not work. Sorry guys. If it's got a combination of those, then the factorials will usually make it work after all. So that's okay. But if it's only rational functions like this, it will just fail. Okay, here we go. The ratio test is designed to compare your series to a geometric series, to the way the geometric series works. Because a geometric series, this is very cool, geometric series has this cool property that if you divide one term by the one before, you'll just get x. So x to the n plus 1 divided by x to the n is x. And if that x is less than 1, then it'll converge. And so what we're going to do is we are going to do that move for our series. We're going to divide each term by the one before, and we're going to hope that that roughly works out to be the same number every time. That's the hope. So this is how it works. You've got your series, and then you do So that's each term by the one before it. That's the goal. So you could do an over an minus 1 if you prefer, but most people make mistakes if they put minuses in at the beginning. So it's totally a thing. Calculate that. You want to do the limit of that as n goes to infinity. And actually you want to do the limit of the absolute value of that as n goes to infinity. So technically you want this. And then, if that answer exists and is less than 1, then it'll converge. I shall call this L. So if L is less than 1, converge. And what that means is that way out there near the end at infinity, approximately each term divided by the one before is L, and so it's approximately L to the power of n. That's how a geometric series works. If you divide each term by the one before, you get the same answer every time, and it's the thing that goes in the spot where the x is. And so approximately, it's a geometric series with the x being less than 1. That's the idea. That's how it works. And if L is more than 1, then it definitely diverges. I'm just going to repeat that. If L is less than 1, converge. If L is more than 1, diverge. And if L is equal to 1, we don't know. There is literally no way of telling from that information whether it converges or not. Sadness. And if you have a rational function that's like Pn divided by Qn, you are guaranteed that the ratio test will produce exactly 1. And that's why it will always fail for that. It will just always happen. It sucks. Do you want an example of this? We've got yes, shakes and nods. I will say one thing about an example for this. So it is very classic that what you'll get is something that has both something like this and like something like this and maybe something like this. It'll have all of those things in it. And so when you do the ratio test, you're going to have to, maybe I'll put a 3 there just to make it easier. When you do the ratio test, you're going to have to cope with all of those pieces. And so you've got your n plus 1 squared through the n plus 1 over n plus 1 plus 3 n plus 1 factorial divided by n squared through the n plus 3 n factorial. So you're going to have something like that. And I have a recommendation, which is to rearrange this fraction. Well, first you normally put this fraction up the other way, because that's how division of fractions works. But rearrange it so that the parts that are similar to each other are together. So this is going to flip because of how fraction division works. And so on the top I'm going to have an n plus 1 squared and an n plus 3. From here I'm going to get an n factorial from here and a 3 to the n plus 1. So all of these things end up on the top. And on the bottom I've got an n squared from here. I've got an n plus 4 from here. I've got an n plus 1 factorial. And I've got a 3 to the n. And what I've done is I put the things that are similar to each other on top of each other. So that the 3 to the things are on top of each other, the factorials are on top of each other, these things without powers are on top of each other, these things with powers are on top of each other. I've done that for a very good reason, and that's because each of these fractions separately, because that's how much fraction multiplication works, I can do that, will have its own limit, and it'll be easier to calculate them separately. Yeah. So this one, I can bring the squared out, and I'll have n plus 1 on n squared. This one I can divide the top and bottom by n. this n factorial, n plus 1 factorial. Well, to get to n plus 1 factorial, I have to multiply everything up to n plus 1, which includes everything up to n, and so that's going to cancel out most of these and leave me with a 1 on n plus 1. Because all of the parts of this that are the bits from 1 to n are included here, so they cancel out. And then 3 to the n plus 1 divided by 3 to the n is 3. Because that's how powers work. And look at that. This limit is 1. Technically I can divide them top and bottom by n if I want. This limit also 1. This limit 0. This limit 3. So the limit as n goes to infinity of an plus 1 over an. Oh crap, should have done an absolute value back there, but they're all positive anyway, so it's okay. Is 1 squared times 1 plus 0 times 0 times 3, which is 0. So tell me, this series, does it converge? Tell me why. Yes, 0 is less than 1. You would probably not be surprised at all that at the number of people who, in a stressful situation like an exam, see the answer 0 and conclude does not converge. Because when they see the 0, they think doesn't exist. But 0 is a perfectly good number which is less than 1. So 0 is less than 1, converge. Yay! So I have a question for you. What would have happened if there was an x in this spot where the 3 is? X there. What would have happened at the end here? You'd still have 0. Yes, there'd be an x in this spot, and it would still come out to 0. And so it would still converge no matter what x is. And that's where the concept of an interval of convergence comes from. To saying, well, if one of these numbers here wasn't, if the base of your exponent, of your power, wasn't a plain number but was an unknown, which x's would make it converge and which ones wouldn't? And in this case, they all make it converge, so the interval of convergence is the entire real numbers. But in some situations, it will only converge for some x's. And I really should have done it with a number that would have worked out. If I didn't have the n factorial there, then I would have just gotten x as my final answer. And in that case, really shouldn't give you the finger. In that case, then it would only have converged if x was less than 1. And it would not converge if x was more than 1. So the idea is if you have a series where you don't know what one of the numbers in the formula is, it will depend on what the size of that is as to whether it converges or not, and the collection of x's that work, that's the interval of convergence. So, but you still do the same process, all exactly the same. Yeah. So today this one worked out very neatly because it worked out to 0 no matter what. But yeah, if this factorial hadn't been there, it would have worked out to a 3, and it would not have converged because 3 is more than 1. Yeah. A useful strategy when you're looking at examples is to do what I just did, to say what would have happened if it had changed in this way? Could I make a different decision? And it means that you can get a little bit more out of it without having to do any more working. Learn a few extra things along the way. Because the human brain in general needs about 7 examples to understand something, and you only usually in your course get 2. And so this is one way of getting some extra examples to make your brain believe that you understand. So there you go. It's my main piece of advice for all maths courses is ratchet in some extra examples. And they are the tests for convergence. So if you see a random series, if it's got powers and factorials, ratio test is the best plan. But the first thing you should do is to just check if it looks like one of your familiar ones. They're the most likely thing to happen. The last thing I want to say, just as a final piece of advice on that front, is that when you're doing intervals of convergence, I'm not going to do the whole thing. Intervals of convergence, you've got like an, but this is like a formula with an x to the n in it. That's what your intervals of convergence are designed for. Cool. You get to see my management team sending me messages. And you're supposed to decide which x's make it converge and which x's don't. Which x's make it converge? The answer to that is the interval of convergence. So, but it is, the theory says it actually is an interval. It has a centre and it has a distance and there's everything from here to here. It will always look like that. It'll always have a centre and you'll go this way and that way on your number line and it'll be something like that. But the question is, does it converge at both ends or at neither end or at one of each? There's 4 options for what could happen. So the thing is that you do the ratio test, and the ratio test will make your limit come to less than 1 inside this interval. And a ratio test will make your limit come out to more than 1 on the outside. But problem is, at these points, the ratio test will come out to exactly equal to 1. And so you won't know from the ratio test whether it converges or not. The only way to tell is to sub in what those numbers are into the formula and see if it's a series you recognise. Yeah. A very, very clever exam writer would have asked you to do a limit, would have asked you to see if a specific series converged in part A, and then the ratio, then the interval of convergence would have had that series at one of these ends, and then you'd go, aha, I've seen that one in part A, it converges. Yeah, but you have to see if you recognise it. There is no other way. Possibly one end will be an alternating series and the other one won't. So usually one end you can use the alternating series test. So one end is usually the alternating series, but they don't usually ask you to do the whole thing. You'll just say it converges because alternating series, and that's enough working. Yeah, but sometimes both ends will converge, and it's quite common for one of them to converge because it's an alternating series and the other one not because it's a harmonic series. Those sorts of things happen. So you can see that if they ask you to make a full interval of convergence, they're already also testing your ability to recognise series. So yeah, though sometimes they just ask you to find just this distance, which is called the radius. Yeah, which happens to be 1 over L, by the way. So that's just a comment about that because it's a thing that's on my mind today. Okay. I know that Taylor's stuff is series-esque, but I might come back to that because I do that most years. So, okay. Might talk a little bit about linear transformations. This one should take about 10 minutes. The specific question I had. I'm very much hoping that this is the question that I had. So linear transformations that are rotations. So here's the thing. I just need to say a couple of things that I hold on to when understanding this. You can write down a formula for what the linear transformations matrix is that goes with its rotation, and that's fine. But I am always worried that I've written that formula down wrong. And so I'm going to show you how to figure it out from scratch in case that happens. Or the worst happens and you lose your cheat sheet on the way to the exam, right, for example, and you have to try and remember without that. I don't want to stress you out by telling you that story, but it is not impossible and has happened before. So, all linear transformations can be rewritten using a matrix. They don't all start out as having a matrix, but you can rewrite them as a matrix. And the name for that matrix is the standard matrix. I'll tell you a secret, there is in fact only one matrix, so it seems weird to call it the standard matrix when it could just be called the matrix, but if you change the coordinate system, then the matrix will also change, and so that's what they're talking about. So very physics, you know, I'm going to put my axes in this spot instead, but the matrix is going to be different now because the axes are in a different spot. That's why it's called the standard matrix, because it goes with the standard axes. So there you go, in case you're ever wondering why. So all linear transformations can be rewritten using a matrix. And the columns of that matrix are what it does to the standard basis. So column 1 is f of, 1, 0, 0, etc. And column 2 is f of 0, 1, 0, etc. And so on. The name for this vector, by the way, is E1. And the name for this vector is E2, in case you were wondering. I don't know why E, but there you go. So if you're in R3, there'll be an E1, an E2, and an E3. If you're in R4, there'll be an E1, E2, E3, E4. In R2, there's just an E1 and an E2. But it is worth pointing out that that is how you can find the matrix for any linear transformation. Some linear transformations have formulas that allow you to find the matrix a different way to that, but this will always work. In fact, in your course, this is defined to be what the standard matrix is, as opposed to the only way to write your linear transformation using a matrix. And the last thing to tell you, which I should have told you second, is that f of vector x is matrix on the left, vector x on the right, and the vector has a column. It's matrix multiplication with the vector on the right hand side as a column. So you have to treat all the vectors as columns for this to work. Even if your vectors are written as rows in the original story, they have to be written as columns for the matrix to work. Okay. This is all stuff that is true about all linear transformations. And this is what I hold on to find linear transformation matrices for rotations. And it's easiest to do with an example. I will read this aloud in a second. Find a matrix for F which sends R2 to R2. Actually, that should be a which is rotation anti-clockwise by pi on 3. If they don't tell you what centre it's rotating about, it's always the origin. And in fact, it will never not be the origin in this course because that wouldn't be a linear transformation. So what I need to do is figure out what that rotation does to the standard basis. So here's my plan. Find f of 1, 0 and f of 0, 1. I'm in R2. That's what I need to do. Okay. Well, there's 1, 0 as a point. And f of 1, 0 is that rotated by pi on 3, anti-clockwise, which is there. And so my output, which I will do in a slightly different colour if I've got one, I am down to green, being the only colour left. Okay. Green it is now. So that green dot there, that is what f of 1, 0 is, because I rotated by pi on 3. And just to be clear, I'll do the other one as well. 0, 1 is here on the y-axis. And then I'm going to rotate pi on 3, which is about here. And that is f of 0, 1. Okay. So if I can find the coordinates at that point, that will be the column I'm looking for. Here we go. Ready? It's so exciting. See this little right angle triangle just here? It's got hypotenuse 1 because this was length 1 and it's rotated. And it's got angle pi on 3. Which means that this distance just here should be cos of pi on 3 because it's on the x-axis. And this one here should be sine of pi on 3. And so therefore, f of 1, 0 will be cos of pi on 3 because that's the x-coordinate, and sine of pi on 3 because that's the y-coordinate. And that is therefore the first column of my matrix. Cool, huh? Are you ready? Ready, ready? Here we go. Here's the next one. This triangle, just here, has an angle of pi on 3 in here. And it's got a hypotenuse of 1. So this here is cos of pi on 3 because it's next to the angle. But that's the y-coordinate because it's on the y-axis. It's cos of pi on 3 because it's the adjacent side. And this is sine of pi on 3 because it's the opposite side. But that's on the y-axis. And so the y-coordinate now is cos of pi on 3. And the x-coordinate is sine of pi on 3. But are you looking? That's a negative number. Minus sine pi on 3. So therefore the matrix is this. And if I could remember what cos and sine of pi on 3 were, I could put it in. Pretty sure that's right. Yep. So pi on 3 is over here. Also, it's a big angle, so sine should be bigger than cos. So, all right. So here's the thing. This will all work if that's a theta, even if it's not a pi on 3. You can put theta in all these spots. And in my memory, if I really concentrated, I could remember this. I could remember that the first column is cos sine, and the other column is the other way around, with a minus. That's how my memory works. I tend to remember one part and how the other parts are related to it rather than remembering the whole thing all at once. But that is how it works. I would like to say to you that any linear transformation, however it is described, you can always do whatever you are told to do to 1, 0 and 0, 1, or whatever the vectors are, like 1, 0, 0, 0, 1, 0, 0, 0, 1, to those vectors and see what the answer is, and then that is automatically what the matrix is. Those 3 columns. So if you're told, find the standard matrix for this orthogonal projection, then you have to orthogonally project 1, 0, 0, and 0, 1, 0, and 0, 0, 1, and that will be what the answer is for the matrix. And if they want a formula for what it does to every vector, that's okay. It'll just be matrix times x, y, z. Sometimes the quickest way is to find the matrix. Is that all right? One of my staff, Adrian, who is my literally oldest staff member, he's 80-something, and he's been working at the Maths Learning Centre for its entire 33 years. This is one of his favourite things to tell people. He will spontaneously tell you without asking this thing. So next time he tries, say, oh, David's already done that for me. Or you could just let him go. Up to you how you want to play it on the day. But it is all based on this idea, which is true for all linear transformations. Yeah. Okay. The person who said determinant and trace, which I think was you, what about it do you want to talk about? Trace. Cool. Well, my first comment about the trace, which will be the comment I leave with you while I'm sharpening my pencil, is the trace is pretty silly. It's a particularly silly thing to do. Why would you want to do that? Some of my mathematical physics friends tell me that it's not silly, but it certainly feels silly to me. So there we go. So don't read too much into it. It's not that deep. So you've got a matrix, right? And it's got numbers in all of these spots. The total of this downwards diagonal is what the trace is. That is, as I said, it's pretty silly. But this is the stupidity of it, and the wonder of eigenvalues is that if you add up the eigenvalues, you get the same answer as if you add up these. It happens to also be the total of the eigenvalues, which was thoroughly unexpected. Eigenvalues also look pretty silly when you define them, okay? Like this whole section to a lot of people feels like random stuff you decided to do to matrices and give them weird names, right? That's how it feels. But any mathematician, once they've learned some of these things, have this weird sense of like wonder and joy at how these stupid ideas are just all connected to each other for no good reason. Like it's just silly, and that appeals to so many mathematicians. But then if you let them talk about it any time, they go, oh, but it's like so deep and like meaningful. It's like, yeah, no, you just think it's fun. So anyway, it is deep and meaningful as well. Don't get any any mathematician who spent any time with eigenvalues to talk about how deep and wonderful they are. I think they are wonderful too, but I'm completely have no illusions that it's pretty silly as well. At the same time, things can be both silly and cool. So here's the thing, that's about it. So thing is, yeah, okay, just also happens to be true if you multiply the eigenvalues, you get the determinant of the matrix. And that was even more unexpected. Like the determinant's this weird-ass calculation where every entry of the matrix is there like 7 times. And then you multiply the eigenvalues together, it's like, wow! And you wouldn't expect them to not be related to the determinant in some way, because both the determinant and the eigenvalues are made from the matrix. You wouldn't expect them to not be related, but this is so simple. And the reason why this is so cute from a maths problem point of view is that if you have a 2 by 2 matrix, you can tell the eigenvalues just from reading the trace and the determinant. So if you've got a 2 by 2 matrix, let me see if I can make one that I know what the eigenvalues are. Cool. Here's a matrix, and its trace is 3 plus minus 2, which is minus 1, and its determinant is 3 times minus 2 minus 7 times 2, which is minus 6 minus 14, minus 20. That's nice and round. Excellent. And I know also that the eigenvalues add up to give this and multiply to give this. That the eigenvalues add up to give the same as the trace, and they multiply to give the same as the determinant. So I have to think of two numbers that add up to give 1 and multiply to give minus 20. If they're going to multiply to give minus 20, one of them is going to have to be positive and the other one's going to have to be negative. And so let's see. 2 minus 1, nope. 3 minus 2, no. 4 minus 5. Aha! There it is. Yay! Same as solving a quadratic equation. Exactly the same. And so we can say that lambda 1 and lambda 2 are minus 4 and 5, since minus 4 plus 5 is 1 and minus 4 times 5 is minus 20. You don't even have to make a quadratic equation, you can just guess. Or, if you weren't in a guessing sort of mood, you could make a quadratic equation. So, you could go, well, lambda 1 plus lambda 2 is 1, and if I times everything by lambda 2, maybe I'll times everything by lambda 1, I'll get lambda 1 squared plus lambda 2 times lambda 1 is lambda 1, but lambda 2 times lambda 1 is minus 20. And so I've got lambda 1 squared minus 20 equals lambda 1, and so lambda 1 squared minus lambda 1 minus 20 is 0, and I can use the quadratic formula to solve it. Yay! Minus b plus or minus b squared minus 4 times minus 20 over 2a. Oh, look at that, it's glorious. 1 plus or minus 9 over 2, and so I've got minus 8 over 2 and 10 over 2, which is minus 4 and 5. Yay! Okay, so wasn't that fun? See, I told you it was fun. It's less fun in an exam, but you know. So I guess all I wanted to say, that's pretty much all there is to it. If you have a 3, yes?
So if we're talking about the set of eigenvalues where the sum is the same and the product is the same, like can we assume that there's only one set that
Okay, so if that sum being a particular number and product being a particular number, and that there's only one set of eigenvalues that do it, that will only work if it's a 2 by 2 matrix. So with two numbers, if you have two numbers and they multiply to give something and add to give something, there is only one pair of numbers that will do that. But if you've got a 3 by 3 matrix that has 3 eigenvalues, then just because they add to something and multiply to give something doesn't mean that the answer you thought of is the answer. But in a 3 by 3 matrix, usually they'll give you one of the eigenvalues. And then you know that the other two, when added to that one, give an answer, and when multiplied by that one, give an answer, and suddenly you're down to the two numbers multiply and the two numbers add. So if your matrix is bigger than 2 by 2, they'll have to give you another piece of information. In the end, if you want to find 3 eigenvalues, you need 3 bits of information. So either you just have the matrix and you just do the work, but it is really common in exams for them to give you another piece of information that tells you what an eigenvalue is. They'll go, oh look, A times this vector happens to come out to 3 times this vector. You go, oh cool, one of the eigenvalues is 3, and I can see the trace and I've got the determinant from some other thing, so you can get it from there. Most of the time, I wouldn't try to do a determinant of a matrix bigger than 2 by 2, unless it's got lots of zeros in it. Because usually they'll tell you a couple of the eigenvalues and you get the last one from the trace. So, yeah. And in fact, that's how I made this one. I knew that one of the eigenvalues was 5, and the trace adds up to 1, so the other one has to be 4. Yeah, because I'm good at making matrices with one eigenvalue that I know. Because if all the rows add up to the same answer, then that's an eigenvalue. So, which is a theorem they haven't told you, but it's a good one. So the 2 rows both add up to 5, so 5 is an eigenvalue. Yay. Okay, so is that enough? Does that make you feel better? Not all matrices. If all the rows add up to the same answer, then that is one of the eigenvalues. And its eigenvector is 1, 1, 1, 1, however many you need. Because if you multiply it by 1, 1, that adds the 2 columns together. It's 1 of column 1 and 1 of column 2. And so if you get 5, 5, then that's 5 times 1, 1, which makes it an eigenvector. Yeah, it's my favourite way of guessing eigenvalues, mainly because the psychology of lecturers making up matrices that have certain eigenvalues. It's the most common way for them to do it. So it's good for exams, not so much for life. But anyway, it's a fun game. Okay, so we did that one, we did that one, we did that one. How about some multivariable calculus? How are we doing? Oh, it's only 20 past, look at that. I'm going to stop talking for a moment and have some water, because we should all have a little rest. I reckon it's the air conditioning making that noise. I reckon it's a water pipe in the air conditioner. Anyway. Oh, it could be. Oh, That's. Okay. Can you just call out some words that go with multivariable calculus, just to get you in the right zone? What? What did you say? Hell. That's all good. I'm going to say a word which is normal and tangent plane. That's a thing, right, in this course? All right, that's plenty to be going on with. Cool. So these are your thoughts and feelings. Okay, so just like ordinary calculus is a way of thinking about the way functions change as you move along them, and they can also allow you to figure out what shape functions are. Same goes for multivariable calculus. And it requires us to think about functions that have multiple inputs and a single output. So with ordinary functions, you have a single number comes in and a single number comes out. You know, something like f of x is x squared plus 3 or something, right? That's an ordinary function. And they have domains and ranges, and you can draw graphs. You can draw graphs and that sort of thing. It's great. This is where the x is, and this is, you say that y is f of x or something like that. Classic. It's great. And you can tell where these turning points are because the derivative is 0 there. F dash x is 0 at that spot. Those sorts of things, we want to borrow those for things that are related to multiple inputs. So this has one input. Because the thing is, most situations that you want to use maths for, especially if you're going to build something or do economics or all sorts of things, have multiple inputs and one output. Like, the tastiness of your cake is dependent on all of the ingredients, not just one of them. Some people think it's just the sugar, but you know, the amount of chocolate you put in makes a difference too. And the water to flour ratio and all of those things. And so there are that's a cooking example, but for economics, you know, there's multiple different industries in a country and blah blah blah. So most situations that you want to use maths for have multiple inputs, and you'd like to know how the output changes when any one of those inputs changes. That's the idea. But also, graphs are wonderful shapes, but they're flat, and the world we live in is not flat. And so we would like to have a way to think about how to draw shapes in 3D with functions and how to tell where their tops and bottoms are. So that's the idea. We're going to try and do what we do in 2D and do what we do for one input functions to do it in 3D and to do it for multiple input functions. And those things don't always link up depending on how many variables are involved, but that's the idea behind it. And so most of these things, it's useful to go back and say, what did that mean back when we were doing ordinary calculus? Okay, so you have a function and it might send r whatever, but let's say r3 to r. And what that would mean is that you have something like f of x, y, z is like some ridiculous formula. Something like that. Maybe we'll times this one by x as well, just to make it fun. I'm not going to try and draw this. You should know that Desmos has a 3D calculator that will draw 3D graphs, if you know Desmos. GeoGebra does too, but I like the Desmos one better. It does less stuff, which means it's less confusing. Yeah, if you go to desmos.com/3D, it's a 3D graphing thing, which is kind of cute. Anyway, of course you won't be able to use that in your exam, but it's useful to see this. So what this is that every point in 3D space has a number to go with it. But it doesn't have to be 3D space at all. This could be the amounts of different ingredients, and this is the rating of deliciousness that your participants give it. And these could be three different components of your chemical process, and this could be what the output is. Like, there's all sorts of things, and two of these could be space and this one could be time. There's all sorts of things you could think of that you could imagine that multiple different inputs produce an output. And so the first thing that we do in multivariable calculus isn't really a geometry thing at all. It's just about how quickly does this change when I change one of these. How quickly does the output change when I change x? That's what a partial derivative is. Keep the y and the z the same and just change x by a little bit. How quickly will that change? And in what direction? Will it go up or down? That, my friends, is what a partial derivative is. So if I said that, if I said df on dx, that is the answer to that question. That is the speed at which the answer for f changes when you change x by a bit. That's it. So if this was the concentration of sugar, and this was the hours you baked it for, it would be moles per hour or something. Like, it's a rate. But if you want to know what it is when you change y, well, that's what df on dy is. If you want to know what it is when it changes z, that's what df on dz is. Curly df on curly dz. So the curly d there is designed to remind you that you're just picking one out of multiple variables. Most people pronounce it as curly d, but technically it's called partial d. Okay. And to do that, you have to treat all the other variables as if they were staying the same, in which case they don't count as variables, they count as constants because they're staying the same. So in this case, df on dx. I'm just going to write f again so it's on the screen at the same time. So I treat everything else as if it was a constant. So the derivative of x squared is 2x, that's great. 3y hasn't got any x's in it, it counts as a constant. When I differentiate, it will completely vanish, because that's what happens to constants when you differentiate. The z here counts as a constant, as does the 7, and so z divided by 7 is currently multiplied by x. So if I just had a number times x, the answer for the derivative would be that number, and so this is that. You're totally correct, thank you very much. Z on 7. That's df on dx. So this is telling me that if x changes by a little bit, then the output will change by this much, and it will be dependent on what x and z are currently. So if z is really big, then this change will be negative and will go down. And in fact, how quickly f changes when x changes doesn't matter what y is at the time, because it's not in this formula. So that's what that's telling me. On the other hand, df on dy is 3, because that's the only one that's got a y in it. So all the ones without y's disappear. So this is telling me that if y changes by a bit, df on dx, by 1 unit, df on dx will go up by 3, or whatever the units it is, no matter what x and z are doing. And df on dz will be nothing there, a minus x on 7. So there you go. Same as with ordinary functions, the speed at which the function changes will be different depending on what the current value of the input is. Speed will be different in different places. Sweet, this is great. If you want a question that want to think about a question which goes, how quickly does the output change when they change x and y and z all at once in this way? That's a different question. But you can combine these together to answer that question. Ready? Just with ordinary functions, just as an aside. Ordinary functions, the change in y is going to be whatever the derivative is times the change in x. That's how derivatives work. If you change the x by a bit, that's the slope, right? So that's how it's supposed to work, approximately. Dy and dx is supposed to be approximately the change in y divided by the change in x. So maybe approximately. Okay? For multivariable functions, the change in f will be I'm going to be dodgy and I'm just going to call it df instead of the change in f. Df to be an extremely small change in f. It will be something times a change in whatever x changed by, plus something times whatever y changed by, plus something by whatever z changed by, or however many variables there are. So if I said, look, I'm just going to increase the flour by like 0.5 gram, and the sugar by 2 grams, and the water by 6 milliliters, how will the output change? Okay? And this is the calculation that does it. And the number that goes in this spot is curly df on dx. This isn't something your lecturers have said, but it is the only way that I can remember how directional derivatives work. Are you ready? So this is saying the change in f will be equal to this. Ready? Watch this. See how this is thing times thing plus thing times thing plus thing times thing? That's a dot product. Look at this. That's a thing. That's the gradient. In this course, the vector which holds all of your partial derivatives is called the gradient vector. Is that what they call it? Do you know why it's called the gradient? Look, look, look. Change in output equals something times change in input. Change in output equals something times change in input. The thing that you would normally put in that spot is the slope, the gradient. So in 3D, the gradient is a 3D vector. I think that's cool. And this is the change in all three of the coordinates at the same time. I think that's cool. It's the only way I can remember it. I have to, it's just stupid. Say, well, there's a bit that's caused by changing x, and there's a bit that's caused by changing y, and there's a bit that's caused by changing z, and we can combine them all together. The way the directional derivative works is saying that if you pick a direction, then this change in x, y, and z will be a multiple of a vector in that direction. Yeah. So that's that. Oh, that's probably confusing. But I am going to just be clear about the directional derivative in just one moment. 11, 12, 13. If that helps you, then hang on to it. So the ultimate goal of partial derivatives is actually to find a directional derivative. So just as a story so far, in fact, new page, because I don't want to be doing this over 2 pages. So we have a function which has x and y and z causing it to change. And we have partial derivatives. df on dx and df on dy and df on dz, that's great. And the gradient, which is a vector which has those 3 things in it. The directional derivative is a number, not a vector. So these are all technically numbers. They're formulas that produce a number. Of f in the direction of u at the point x. Do they give a symbol to this? Like, is it like an upside down triangle? No? I feel the need to look that up. Just one moment. Come on. Yes, they do. That symbol. Most people pronounce this symbol as del. It's an upside down delta. But anyway. So, the directional derivative of f in the direction of u at the point x is defined to be this. That's the symbols. And the definition is the gradient of f dot with u. And what's going on is this thing here. The u is at that spot. That's the gradient, and that's the u. But it'll only work if the u is a unit vector. That's why it's called u for unit vector. So the reason I've said this, like if I said I wanted to change, sugar by this much and water by this much and flour by this much, I would have to imagine that as a vector in 3D space and find a unit vector and dot it with the gradient, and that would tell me how quickly the output changes when I move in that direction. So some people think about this, and I'm going to pull off of the cooking and go to temperature. This room, every point in the room has a temperature. I could imagine a formula that if I put in the XYZ coordinate of this point, it would tell me what the temperature is at the moment, and this one, and this one, and this one. And if I want to know, if I head in that direction, I need to know how quickly the temperature is going to change if I go that way. And so I get the gradient and I dot it with a unit vector in that direction. I should have done that under here, but anyway. I want to go that direction, and then I need to figure out what the gradient is here and dot it with that direction. And that will be a number. It'll be the speed at which that thing changes when this changes by 1 unit per second or whatever. So you need a unit vector because what you're doing is marking out a new x-axis along that direction. And so you need to know where the 1 and the 2 and the 3 are on that axis. So, yeah. So this is one of the more complicated things you can be asked to do, but the answer at the end is a number. So you can imagine at a specific spot, if I think about the temperature as I move past this point, that if I move past it in some directions, the temperature will be going up. If I move past in other directions, the temperature will be going down. If I move past in some directions, it will be going down even faster. And out of all of the possible directions, so if I go this way, maybe the temperature is going up. If I go this way, the temperature should be going down. Somewhere in the middle, as I move past it, the temperature shouldn't be changing. Because going up this way and going down this way. So somewhere in the middle, if I go that way, the temperature shouldn't change if I go that way. Right? And that's interesting. And one of them, out of all of the directions I go, should be the fastest. And this is the magic trick. It's an extremely excellent magic trick. The direction you should go, see, this isn't just a handy place to hold your derivatives. You can also interpret this as a direction, and if you go that direction, it's the direction to go to increase the speed, to increase the f the fastest. So, direction to go to get the highest directional derivative, i.e. increase f the fastest, is the direction of the gradient vector. So you reinterpret that vector as not just a handy place to hold the derivatives, but also interpret it as a direction, and that is the direction to go to get the highest directional derivative. And even better, the magic trick is better than this. What the actual answer is for the directional derivative in that direction is the length of this vector. Which is just super duper magic trick. So you can imagine a physicist who is thinking about, you couldn't, but I'm going to make you imagine it. Imagine a physicist who's got a nice little formula that tells him what the electrical field strength is at every point in surrounding a coiled wire that he's made. There's a formula for what the electrical field strength is, and your physics team is going, okay, so if I put a charged object here, which direction will it go and how quickly will it move? Cool, I'll just find the gradient and find its length. It's amazing. Yep.
Is that f or a partial in the direction?
This is the length of the gradient of f.
Okay, yeah.
So that gradient vector up here, you do the, square all of them and add them up and square root, and that is the answer for the directional derivative, the highest possible directional derivative. Just amazing. I've always been something that I go, that's cool, even though I have no use for it in my life, even as a mathematician, because I don't work with real numbers. But I just think it's cool. So, but it is totally a magic trick, right? There's a good reason why it works, and you can go through the maths and do cosines and dot products and stuff. There's a proof for why that is the truth, but it's very clever. Yeah. Okay, so that's all the partial derivative stuff except for, nearly there. The other thing we use derivatives for is to figure out where maximums and minimums are. And you can think of them as surfaces and having them having hills and valleys, but you can also think of them as this whole room has temperature, where's the maximum temperature? Theoretically, it should be the place where no matter the direction you go past it, you can't make the temperature any higher. Right? That's where the highest temperature is. And if you can't make the temperature higher as you go past that spot, then that means the temperature is not changing as you go past that spot, because it can't get any higher. So what that means is, but also on the top of a hill, if you can't make it higher, then the height at that spot, at the very moment you're passing it, doesn't change. So for maximums and minimums, you need that no matter which direction you pass that spot, that the derivative is 0 in that direction. So you need all directional derivatives to be 0 as you pass a maximum or a minimum. Because that's how derivatives work. You know that derivatives are 0 when you're passing a point that's a maximum or a minimum. So if it's a maximum minimum in space, you have to pass in no matter which direction you go, it has to be a maximum in every direction. Okay, but if all of the directional derivatives are 0, and you make a directional derivative by dotting with gradient of f, that must mean that the whole gradient must be the 0 vector. If every possible direction gives you 0 when you do this dot product, that must be the 0 vector. So yeah. So that is, you need the gradient of f to be the 0 vector. Which means you need df on dx and df on dy to be 0 and df on dz to be 0, all at the same time. So it's kind of cool that you need all the derivatives to be 0 in every possible direction, but you actually only need 3 of them because that'll make all the other ones 0 because of the way the calculation works. So it's pretty cool, actually. So now if that means that if you want to find a maximum or minimum, you need to find all the partial derivatives and you need to make them all 0, and they need to all be 0 at the same time. And if you can find that point, that's where the maximum or minimum is. And there may be several of them. There may be none of them. I wonder if this vector we had earlier is function we had earlier has any good ones. Oh yeah, see this function we had earlier? That has no maximums or minimums because it's impossible for df on dy to be 0. It's always 3. So I'm just going to pop that example down. So e.g. f was x squared plus 3y minus zx on 7. df on dy was 3. Impossible to be 0, so there are no maximums and minimums. But most of the time there's more than one. Let me see if I can find one that has actually several. Well, let's see what happens. Okay. So dg on dx is, alright, so if this was a number, it would be left behind because x times a number, so that would be y plus z plus 2x. df on dy is x, because the x will still be there because it's multiplied on, and then the derivative of y is 1, and then df on dz is, the x will still be there because it's multiplied on, derivative of z is 1. Okay. Oh well. So we need all 3 of those to be 0 at the same time. Okay, so we have y plus z plus 2x is 0, x is 0, and x is 0. And I can sub these into there. Y plus z equals 0. And so I get y is equal to minus z. And that's the best I can do. And so any point that has 0 for x and minus z for y and z for z is one of those places. These are called critical points, by the way. So if there is a maximum or a minimum, if there are any, it's one of those. Don't know which one, or if any, might not be any of them, but they are the critical points. It is much more common to get a couple of points at the end. How would I change this so it came out to something? Bear with me. Let's try that. Oh crap. This is why they take weeks to write the exam. I want to sit there 10 seconds before. This is going to come out to have an extra plus 1 in the derivative of y, which means that x is going to have to be simultaneously x equals 0 and x equals minus 1, and that's impossible. So just to be clear, dg on dx is y plus z plus 2x. dg on dy is x plus 1. dg on dz is x, and this is equal to 0, this is equal to 0, this is equal to 0. That means that x is minus 1. That means that x is 0, and you can't have both of those true at the same time. Okay, so look, there's another way for it to be impossible. that the only way to have all three of them 0 at the same time is to have x being two different numbers at the same time. So I would have to go look up an example to try, I'm sorry, and I choose not to do that at this time. But it is very common to sub one of them into the others. Yeah, and sometimes you won't get an actual number for one of them, you'll just get a formula for x equals something in terms of z, and you'll sub that into the other one until there's only one variable left. And it's very rare that it will be the sort of equation you can use row operations on, because it's usually got some squares and stuff in it. So the sneakiest one I've been given is one where there's a quadratic equation for one of them. It gives you two answers for x and y, and when you sub for x and then you sub that in, and you get two answers, the matching answers for y and z, and so you get two different answers at the end. So sometimes you get a list of x's. Yeah. Ugh. Okay. Now, I'm almost there. For maximums and minimums, how do you decide if they are a maximum or a minimum? Sorry? That's a phase line would be great if this was a differential equation, but it's not. Well, in ordinary calculus, sometimes people use the second derivative to tell you what a maximum and minimum is. In ordinary calculus, you'd use like not a phase line, but a sign diagram. That's the word for it when you're not doing differential equations. Totally would work. But if you're in 3D and you have a point here in the middle of nowhere, now it's on camera, a point here in the middle of nowhere, and where are you going to put your plus? And does that mean like all of this is plus? Like where's the divide? Oh crap. So not going to happen. So what you need is something else. And so in first one-dimensional calculus, sometimes you use the second derivative to tell you whether you've got a maximum or a minimum. And if the second derivative is positive, that means that the slope is going from negative to positive, and so that means it's a minimum. And so we can do that in 3 dimensions. We do it when there's only 2 inputs. There is technically a way to do it with 3 inputs, but they don't teach it to you. But you know, telling if a maximum or minimum, you use the second derivative. But there's 2 variables, so you use the second derivatives. So imagine this is your function, and it's got an x and a y, and they are both telling you how f changes. If you differentiate again with respect to x and y, then you will have the second derivative. So you can have df on dx, and then do d on dx again, and that would be d squared f on dx squared. That's the second derivative with respect to x. And you could do df on dx and do d on dy of that. That would be d squared f on dy dx. Or you could df on dy and do d on dy of that. That would be d squared f on dy squared. And technically, you could do df on dy and do df on dx of that and get d squared f on dx dy. Turns out that for almost all functions, you actually have to work really hard for these to be different, and it is almost always true that these are the same. Like the only way to make them different would be to cook up some crazy function that had different formulas in different places. like with one of those big branchy things. So those are the same. I should tell you another notation for this. It is worth noting that this is f differentiated with respect to x and then x again. And this one is f yx, and this one is f yy, and this one is f xy. Again, it does technically matter which order they're in, but the answers comes out the same anyway, so it doesn't matter. But like when you're doing d on dx's, the new ones go on the left, and when you're doing subscripts like this, the new ones go on the right. So mathematicians were a bit upset about all of the multivariable calculus notations and how they're all different and how they don't make any sense. And there was a conference set where they would all meet together, mathematicians from all over the world, to fix the notation for multivariable calculus. And that conference was set for 1914. And the First World War happened, and so the conference never happened, and so our notation still sucks. Okay, so when you do that second derivatives, it's weird and basket case, but you have to do a determinant of fxx and fxy and fyx and fyy and do this determinant. And that will tell you whether it's a maximum or a minimum. Well, actually it won't. That will tell you whether it's a maximum or minimum or neither. A saddle point, which is a maximum in some directions and a minimum in other directions. And so if this comes out to positive, then it's a maximum or minimum, but you don't know which one it is yet. And if it comes out to negative, then it's a saddle point. And if it comes out to 0, then nobody knows. It could be anything. And after you've decided if it's a maximum or minimum, then you'll look at one of these two. And if it's negative, then you're saying, well, if you go, then in that direction, it's one-dimensional, and so that would make it a maximum. So fxx negative would mean it's concave down, which means it's a maximum. Or ffy, fyy. Or if fyy, that's not a divided by, that's an or. Positive, that means it's concave up, and that makes it a minimum. But you can only do that after first doing this. This is all in here, right? Good. Just making sure it wasn't something that wasn't in the course. Yeah. So anyway, I wouldn't expect your lecturer to put this in your exam. You never know, though. So, point is, though, you can't just base it on this. You're going, oh, why can't I just look at fyy and go, oh, that's negative, so it must be concave down and therefore be a maximum. But the thing is, in the x direction, it might be a minimum. And in fact, it may be that both of those are maximum, and then somewhere in between, it's a minimum. And so you don't know where the saddle in the saddle point is, and so you have to check that it's not a saddle point before you make this decision. So if it's not a saddle point, like if this is positive, then that means that if it's concave down anywhere, it'll be concave down everywhere, and that will be a spot where it's a maximum. I know we're officially finished, but I did want to say one more thing while I'm on the thing, because I don't want to miss anything. So there is one last thing, which is the multivariable chain rule. And the multivariable chain rule says that if you have a function which is a function of two other variables, and they are also functions of other variables, then you can do the chain rule. So here's my story here. I've got that z is a function of x and y, so z is like, and then x is like a function of u, and then y is a function of u and t, something like that. And this is a diagram of what's going on there, saying which variables cause the other variables to happen. And this diagram tells me how the multivariable chain rule works. Are you ready? If I wanted to do dz on du, okay, there are two variables that cause z to be what it is, u and t. Then I could come down these paths. So I'm going to find the paths that go to u. There's one here and there's one here. And so dz on du, first I'll go to x, down that path, and I'll do that derivative. And then I'll multiply down this path. And that's a straight one because du, there's only one variable there. So I don't use a curly one there because there's only one variable going to x. But then I also have to come down this other path and going dz on dy and then dy on du. And that one's curly because y has two options. And dz on dt, well, this path doesn't go to t, so I don't have to worry about that. And it will be dz on dy times dy on dt. I don't have this one because it doesn't go to t. Yay! That's how it works. Sometimes they'll just tell you what these numbers are at specific spots. Sometimes they'll give you formulas for some things in terms of other things. Sometimes they'll do a mixture of the two. But the thing that helps me hold on to what I'm doing with the multivariable chain rule is drawing a diagram like this. And it can be as complicated as you like. And it can sometimes be that z is made of x and y, and x is a function of y. And that'll be okay. Because just follow it through. It'll be fine. So, yeah, this tells you how the subbing in works. So if they tell you u and t, then you can sub them all in to figure out what x and y is, and then sub the x and y in to figure out the z. The whole point of the multivariable chain rule is to not have to sub in the formulas and to be able to do each step separately. Yeah, and if there were three variables, then there'd just be a plus for all the other paths that go to the places. I am completely in love with this when I learned how to do it, and it made me stop worrying so much about this thing. And this is in fact the same as how the gradient vector works, because you can imagine way back here. Where did I put it? Not that one. If you put a on dt for all of these, that's just the same as the multivariable chain rule. Thinking about f being a function of x and y and z, and each of those being caused to change by time. You can go df on dt, and it's this times dx on dt, this times dy on dt, this times dz on dt, which I kind of like. Anyway, that makes me feel happy too, because I'm thinking about, when I think about the gradient, I'm thinking about moving this at a speed, and so there's always a time involved. Rightio. I didn't talk about surfaces, but it's really time to stop now. There's at least 2 staff in the Maths Learning Centre every afternoon until your exam, which is, I know, only 3 afternoons, but we'll be there. And there's any number of past revision seminars. Right, I should stop the recording.